Yes. So we are live. Let's admit everyone, and in 1 minute we can start. By the way, Lieven, let me just clarify that we are very informal and we don't make very flamboyant introductions, so we go straight to the point. I hope you don't mind.
Sounds good.
All right, it's 3 p.m. Time to start. Welcome back, everyone, to another Quantum Matter seminar. It's my pleasure today to introduce Lieven Vandersypen, who's going to be talking about some beautiful experiments. Before we start, let me just make sure that you all can interrupt at any time. Feel free to unmute yourself if you have questions. Let's try to make this session very interactive, if possible, to make it more lively and exciting. And of course, you can also ask questions on the chat. And if you prefer that, I will read the questions to the speaker at the end. All right, so let's get started. Please, Lieven, go ahead.
All right. Well, thanks, Adrian. Thanks for the invitation, and glad to get this opportunity to tell you online about some work that I've been involved in for more than 20 years on quantum computing and more recently quantum simulation. It's something that continues to motivate me, to drive me, and that I think that I'm also increasingly optimistic about what it's going to bring us eventually. So if we, let's see here, yeah. So if we take physics courses, specifically quantum mechanics, at some point, perhaps one of the earliest things even is to study the energy level spectrum of the hydrogen atom, where a single electron orbits around a positively charged nucleus. And it's actually an exercise, as you know, that we can do with pen and paper. With a bit more work, it's even possible to describe electrons in semiconductors like silicon or metals like aluminum. And in this case, the properties are described by the band structure. And the reason why we can do this efficiently and rather easily is that to good approximation, we don't need to treat the electrons as interacting particles. So basically a single particle description works well, and we only need to worry about the effect of the underlying lattice of positively charged atoms. Now, as you know, this picture is quite different in important problems in quantum chemistry and material science, where the interaction between the electrons are really fundamentally and profoundly impacting the properties of the molecules and of the materials. And so there's a major drive in condensed matter physics to try to compute the properties of molecules and materials using massive supercomputers. But in all cases, or in many cases, one needs to make approximations, and there is no efficient path to precise solutions. And this has left us with, catalysts or fertilizers that are not yet optimized as they could be. It leaves us with still a puzzle on the mechanism behind superconductivity at high temperature, at room temperature. And for the moment, no means of seeing room temperature superconductivity seeing no superconductivity at room temperature except under extreme conditions of pressure, for instance. Also, there is a desire to understand if batteries or perhaps certain ways of harvesting solar energy can be made more efficient if we were able to better understand materials properties. And so what's common in all of these cases is that contrary to the hydrogen atom or to the band structure of silicon, now the interactions between the electrons are really crucial for understanding the properties. And in this case, you know, the Hilbert space explodes exponentially as you add particles, and it quickly becomes a problem that's intractable for all practical purposes. What's remarkable is that at some level, it doesn't even matter whether you're doing this computation on a mechanical machine or an abacus or on a modern supercomputer, because in both cases, the computation is restricted to working with the classical laws of physics, Newton's laws, Maxwell's laws of physics. And, you know, at some point, information is encoded in a 0 or a 1, and it has to be either 0 or 1. You're computing with states or with bits in a definite state. And there is so-called universal models of computation that describe any machine that we can use to compute. At least so we thought until you know, more recent years, when quantum mechanics became manifest not just in the behavior of single particles such as atoms or photons or electrons, but were even microscopic currents of electrons flowing through, for instance. And can you see the cursor? Well, I think I can do this better. Let me do this here. I think now you can see here my cursor on the screen where flows of electrons are moving through this circle-like structure, and where the interference pattern as a function of the magnetic field applied perpendicular to the ring indicates that every single electron actually in parallel or in superposition passes through the two branches of this ring. And so if this is true, you know, could we build electrical circuits that then operate in a quantum way, and that perhaps can offer possibilities for computing that we haven't seen before and that are perhaps much more powerful. And of course, Feynman has speculated that indeed a so-called quantum computer could solve problems. He referred to problems in chemistry or material science governed by quantum mechanics, could solve problems much more efficiently than any classical computer would ever be able to do. Since these first ideas, there has been a lot of work, both theoretically and experimentally, in this field of quantum computation and simulation. And by now it's clear that really, you know, a quantum computer, if you could build one, indeed would be an extremely powerful machine, and it could help us predict materials properties better, problems in quantum chemistry, mathematical problems that have impact ranging from energy to health and security. And you know, if you look at the more recent developments, there is speculation about a wide variety of problems that perhaps could be accelerated using quantum computing, quantum technology over machines restricted by the classical laws of physics. So this you know, important expectation was, I think, described quite powerfully by the Nobel Committee in 2012.
Hello?
Yes, please.
Good afternoon, Mr. Richmond.
Yes.
Oh, and I think somebody's having a parallel conversation. If you could.
Oh.
Yourself.
Can you call me back in about an hour?
I won't be in the office at that time.
Okay, so now I need to unmute myself. Good. All right. So the Nobel Committee, in their statement 8 years ago now, when they awarded the Nobel Prize to Horseridge and Weiland, stated that the quantum computer may change our everyday lives in this century in the same radical way as the classical computer did in the last century. And you know, the impact of classical computers has been really enormous. You know, so the expectations here are set quite high, but certainly I think there is reason to believe that using the quantum laws, you can do really significant things. So, oh, hold on. Yeah, all right. you know, if you read the newspapers nowadays, you would almost believe that there are quantum computers today that are commercially viable and that can solve relevant problems, or if they're not there today, perhaps they're just around the corner. In reality, I think a lot of work remains to be done, and what we're after is a challenge that's really a very difficult one. And it goes, I'd like to go back to the same Nobel Prize, because really what is needed to build a quantum computer, to build quantum technologies in general, is to be able to take individual quanta, you know, whether it's, let's say, the position of an electron or the state of a spin of an electron, perhaps a phonon, any excitation at the quantum level in principle can serve as the basis for a quantum bit, but you have to be able to initialize and control that excitation, that quantum of energy. You have to be able to read it out, to couple it to other quanta of the same kind in order that you can compute with it. And that is actually very difficult to do on a large scale. And so we have to face this fact that even though, you know, in the experiments, for instance, by Harosh and Wineland and many others, it's been possible to control individual particles. Doing this on a large scale with many particles that interact and maintaining control of the time evolution and being able to read out and so forth is really a formidable challenge. Now, in my mind, a major advance in our field of quantum science is that in the last 2 decades or so, and it really goes back to before that, to the days of well, the days aren't over, but let's say to the origins of mesoscopic physics, it's now possible to design structures on a semiconductor substrate made from semiconductors, metals, superconductors, where quantum effects can be very prominent, where they can be controlled and probed at the level of individual quanta. In other words, it's now possible to realize quantum bits on a chip. And there are a variety of ways of doing so. There are the very successful experiments on superconducting circuits that are the ones based on impurities, for instance, hosted in diamond. There are hybrid structures that can give rise possibly to topological excitations and topological qubits. And finally, there are semiconductor quantum bits, often in the form of semiconductor quantum dots, which are, which is a system that I work on myself, and which is, I would say, my favorite system. And so what I would like to do is to tell you about our work on trying to realize a prototype quantum computer that has all the potential for scaling to the large numbers so that it can be fault tolerant. And what we mean by that is, any quantum bit or any quantum system that you try to control has a finite coherence time. The state is preserved for a finite amount of time. Depending on the system, it can be an attosecond or it can be a second, but it's finite. And furthermore, if you try to operate on it and manipulate its state at the quantum level, you never do this with 100% accuracy. And so if these manipulations are steps in a computation, they accumulate, well, they lead to errors that accumulate. And so the question then is, can you remove those errors and the errors arising from decoherence? And in principle, that can be done, but it requires a large overhead. It requires a lot of redundancy. So that's the first direction that I want to talk about. Can we build quantum computers that function well, even though the constituent quantum bits are subject to errors like any real system? And in the second part of the talk, I want to tell you about our efforts to use the same system of quantum dots to mimic quite directly relevant physical systems and a field that we call analog quantum simulation. So this is not about building a computer and programming it, but it's about building a model system that emulates physics that you like to understand better. All right, and again, I do welcome questions along the way. So looking now at the field of spin qubits and quantum dots, I think we can say that there has been a first wave of development, let's say from the year 2000 through, let's call it 2010, where all the basic concepts had been tested and demonstrated experimentally in the lab. And it starts on the top left with the ability to build quantum dots. And actually, I'll maybe go back for a moment to this image here and then comment a bit more on how we form these quantum dots here, right? So what you're looking at here is a scanning electron micrograph showing a pattern of metal gate electrodes on top of a semiconductor heterostructure. In this case, it's a gallium arsenide, aluminum gallium arsenide heterostructure where some 100 nanometers below the surface, the interface between these two layers exists. And these structures are typically doped so that you get electrons that can move around. But because of its design, the motion is confined to a two-dimensional plane at the interface of the gallium arsenide and the aluminum gallium arsenide. So that's the starting point. And then with negative voltages applied to the electrodes on the surface, we can repel electrons underneath the electrodes. And in doing so, and by tweaking the voltages in the appropriate ways, we can, in the locations of these circles, create local potential minima, where one or more electrons can be trapped. And these potential minima is what we call the quantum dots. They are small enough. You see the scale bar there. Sizes are tens of nanometers, 100 nanometer. They're small enough so that at low temperature, we operate in dilution refrigerators at 20 millikelvin. At low temperature, the number of charges is very well defined. And furthermore, you even see the quantized orbital level spacing arising from the confinement at these sufficiently low temperatures. So with this type of system, it's become routine now to go to the regime where we empty each of these quantum dots all the way until there is just exactly one free electron left in each of the quantum dots. And then the spin of each of those electrons will be a quantum bit for us. The way that we read out a single spin is as follows. The signal from a single spin, the magnetic signal, is extremely weak, and it's very hard to detect on a time scale faster than the time that the electron spin will spontaneously flip, by coupling to its environment. So instead, what we do is the following. We make the electron, well, we apply a magnetic field, and then you have an energy difference between the spin up and the spin down state. That energy difference is always there from the magnetic field. And then if the electron is in the lower energy state, in the spin down state here, we have aligned the energy level of the spin up electron here in the quantum dot such that it does not have enough energy to pass through the tunnel barrier and go to the empty states here above the Fermi level in the reservoir. Whereas if it's in the opposite state, in the spin down state, it has more energy. It actually has enough energy to access the empty states available here in the reservoir. In fact, after that happens, another electron is going to enter the dot and fill it as a spin-up electron. But for a brief moment in time, the dot will be empty. And while this happens, we record using a charge detector. And the charge detector in this case is the current through another quantum dot nearby. We notice that this current is modulated by an appreciable amount anytime a single electron enters or leaves one of the dots or moves from one dot to another dot. Each of these events changes the capacitive coupling that this electron has to the sensing dot and is picked up. And we can pick it up in real time on a timescale compatible with the timescale needed for spin readout. And so in one case, we get a little blip telling us that the spin state before measurement was down. In the other case, we don't get a blip telling us that the spin state was up. Once we know how to read out, and we can also initialize states, what we can do is to probe how long it takes for the spin down electron to relax to the ground state. And that timescale is actually quite long. It can be up to a second or even more than a second. This is a timescale that we call T1. So then the next step, of course, is to coherently manipulate the state of the spins. And in 2006, in our group, we showed for the first time coherent control of a single electron spin in such a quantum dot. And that was by applying an AC magnetic field that then created the conventional magnetic resonance conditions to rotate that spin. And the measurement here shows these oscillations. It's measured in the form of a current, and I'll skip the details, but these oscillations reflect the oscillation of the spin in what we call the Bloch sphere. So from spin up to spin down and back periodically. The next year, actually, we've shown that it's also possible to drive a single spin using electric fields rather than magnetic fields in 2007. And here, the electric field is able to talk to the spin through the spin-orbit coupling that exists in the host semiconductor. So that actually allows us to drive spins also electrically. In the meantime, the Marcus group at Harvard had shown that if you allow electrons in neighboring dots to have overlapping wave functions, so you basically lower the tunnel barrier that separates the two dots, and you allow the wave functions of the two electrons to overlap, then a spin exchange Hamiltonian will begin to act on the spins, and the effect of that spin exchange Hamiltonian is literally to exchange the two spins. So if you started in an up-down state, after half a period you end up in a down-up state, and then after a full period you go back to the up-down state and so forth. So in both cases, it was possible to measure the spin dephasing and coherence time, and these timescales actually were very short, many orders of magnitude shorter than the T1. This is now about the timescale on which you lose track of the phase of the qubit. So it's not the population difference between the excited and the ground state, it's really the quantum mechanical phase between them. And so that dephasing occurs without any special measures. It occurs on a timescale of tens of nanoseconds. And the main origin for this is that in this gallium arsenide substrate, every gallium and arsenic atom itself has a spin attached to its nucleus. And through the hyperfine coupling, all of these nuclear spins, which are randomly oriented, are coupled to the electron spin, and they basically act like a random field on the electron spin. And if you have a random field acting on an electron spin, it's going to evolve at a random precession rate, and you lose track of where it's going. So this was the first wave of spin qubit development based on gallium arsenide. In my mind, this was kind of a dead-end road because of the short dephasing time, but all the concepts were shown to work. Now the field got a second boost when, as a community, we learned to build suitable quantum dots in silicon and even build isotopically purified versions of this, where the silicon-29 atoms that also have a nuclear spin are largely eliminated, and mostly what remains at the location of the quantum dot is silicon-28, which has no nuclear spin. And so this problem of hyperfine induced dephasing is immediately gone. So moving to silicon brought us a factor of 100 improvement in T2 star, as we call it, this spin dephasing time. And moving to purified silicon, even 4 orders of magnitude, so 10,000 times longer dephasing time, from 10 nanoseconds to 100 microseconds, as shown in this experiment from the Zurich group. In the meantime, very high quality single qubit rotations have been demonstrated. We express this in terms of fidelity. You know, basically, it means you perform an operation, and after the operation, you project in some basis, and what is the probability that you get the expected, theoretically expected or desired outcome, and what is the probability that you get the wrong outcome. For single qubit, single spin rotations, the error probability is now less than 0.1%. For 2-qubit operations, the published work from ourselves and the Zurich group is between 92 and 98%. But anytime I expect a paper, and it might be us or someone else, that shows 2 nines of fidelity, and I think that's imminent. And with more work, we're also going to hit 3 nines of fidelity, so 0.1% errors. These numbers, to put them in perspective, have to be compared with the error rate that you need to correct the errors faster than they occur. And that threshold is around 1% error. So you need to do better than 1% error. If not, then there is no hope, at least not with the commonly considered error correction techniques. There's no hope of correcting the errors faster than they accumulate. But here it looks like, well, in part we're doing this, and in part this is a matter of time before we'll do this more extensively. With this system, we have also shown that we can entangle 2 spins, as have other groups, and we've even taken the step to program a variety of simple algorithms, very simple, acting on 2 qubits. Grover's algorithm, the Jose algorithm, acting on 2 qubits, hosted by spins in silicon. This was very satisfying for me to see that we had reached the level of control that we can really program it and do anything that we want. So from there, the vision that I have, with others in our field for moving to the really large scale is as follows. I think we'll be able to integrate 2-dimensional arrays of quantum dots, but I also think that in practice, there will be a sort of optimal size of these local 2-dimensional arrays. We will not probably go to 1 billion. I mean, they're very compact. With the pitch of 100 nanometer that they have, there is room for a few billion quantum dots or qubits in an area of just a square millimeter. I don't think that's the way we're going to go. We'll have local registers of some size, and I don't know yet what size. And we will connect them with other local registers of qubits on the same chip using quantum links. And I'll tell you about our efforts in building these links. And furthermore, if we have millions, because that's the vision, we expect that we're going to have millions of qubits on the same chip, we don't expect to bring millions of wires to that chip. A modern processor or memory chip has a few hundred to a few thousand pins to the outside world, even though there are billions of transistors on the chip. And so similarly, when we build large-scale quantum circuits, I think that we'll need a means of bringing in a number of wires to the chip that is much smaller than the number of qubits. And then on the chip, we'll distribute the signals using some multiplexing and other electronics. That itself poses, of course, its own challenges. But in the end, I think the spins in quantum dots are well placed to make this happen. As I'll show you, the qubits can be relatively resilient to temperature, allowing integrated electronics on the same chip. Furthermore, the technology is semiconductor technology. I'll cover that. And that allows, again, co-integration of classical electronics and qubits. The pitches can be very high, so we can get really many qubits on a reasonable footprint. And finally, as I've shown you, the intrinsic coherence of these spin qubits is really very high. Oh, I didn't emphasize this even, but from the 100 microseconds time scale that you get from just letting the spin sit by itself, that can be extended to tens of milliseconds using extensions of so-called spin echo techniques. These are techniques that allow you to reverse dephasing due to systematic but unknown contributions to your magnetic field or Hamiltonian in general. So let me now tell you about each of these three aspects: local registers, quantum links, and integrated electronics. So the quantum link, the local registers, we are now in the process of measuring devices with 3, 4, 5, actually also 6 dots in linear arrays. We're doing measurements on 2x2s and have made initial attempts at 3x3s. And the vision eventually is that it may be possible, once we reach sufficient homogeneity, to have 2-dimensional arrays where we no longer need to bring a single wire to each of the quantum dots, and instead can control them using so-called crossbar addressing schemes. So just a grid of vertical and horizontal lines like are used in touch screens or displays or memories today. In order to do that and build large circuits that all operate, I'm quite convinced that we are going to want to use cleanroom facilities, not university style. University style cleanrooms are optimized for flexibility, for creative ideas, trying new things, but rather to use industry facilities. And a good 5 years ago, we started a very close collaboration with Intel. It's very interactive. We talk every Friday, exchange updates, brainstorm, talk about the next steps, report results back and forth. And it's really geared at trying to make quantum bits, spin qubits, in an industrial facility at Intel in Oregon. So, and I'll show you where we are. What you see here in the cross-section, this is a cross-section of a set of gate electrodes that run on top of a fin that creates one-dimensional confinement. And using or applying the right voltages to these gates, just like we do in our own structures, it's possible to create an electron landscape where you confine one electron in each of these potential minima. That's the idea. The top view looks like this. So the cross-section here comes back over here. These are the gates. And then there are the contacts at both sides. You see the fan out of the gates. And then opposite, you see a second set of similar gate electrodes. These we're going to use to sense the qubits in the first row here. And so this is an actual image from a device made in the Intel clean rooms on wafer scale. So these are 300 millimeter. What is it in inches? I think it's 12 inches, isn't it? 300 millimeter wafers. There are some 10,000 test rows on a single wafer. That translates to hundreds of thousands of quantum dots, more than we can ever measure in our lifetime. But the important point is not the quantity, but is the way they are made. And as you can see, the cleanliness of this structure and the homogeneity of these two different, well, there's two sets of gates here, the ones labeled in red and in blue, but all the blue ones look really quite homogeneous. All the red ones look quite homogeneous. And that is really no comparison to a TEM image of a device that we make in our clean room in Delft. And I have to say, we have an excellent clean room, but the homogeneity and the control, there is no comparison. And so ultimately, to make a large scale circuit where all the components work and where there is sufficient uniformity, I think we're going to have to rely on these processes like at Intel. However, it poses its own challenges. You know, electron beam lithography, it's very flexible. Lift-off processes like we use are very gentle. In contrast, these super kind of controlled and rigid and uniform structures require a completely different way of fabricating the devices. Very aggressive etches, chemical mechanical polishing. It requires a lot of metal that has no function other than allowing the fabrication to yield. That creates its own challenges. And so altogether, it's been a process of several years, but now I'm happy to show that happy to show that we can now build quantum dots where we can control the occupation in each dot with great precision. We can control the coupling between them, and the yield and uniformity are really quite high. And furthermore, and this is really very or more recent and not yet published, we have seen that the quality of the qubits, despite the very harsh processing conditions, actually matches those that we obtain in university-style clean rooms. So here you see an example of an oscillation of a single spin, you know, in silicon 28, in the silicon 28 substrate fabricated wafer scale at Intel, and all of the characteristic timescales are quite respectable and comparable to what we can what we can achieve with academic-style one-of-a-kind devices. So moving now to our approaches to realizing these quantum links that are supposed to create entanglement, distributed entanglement between different local registers on the same chip. We follow two approaches. One is inspired by the work of the superconducting qubit community, where we have a superconducting resonator that couples to a single spin. That in itself is again hard to do. You know, I have to say one more thing. What couples to the spin is a single, or what we want to couple is a single microwave photon trapped in this on-chip superconducting resonator. And we want that single photon to couple to our spin sufficiently strong that the coupling strength overcomes both the dephasing rate of the spin and the decay rate of the cavity. And if you work out the coupling strength between between the magnetic field of such a cavity and a single spin, again, that gives you a far too low number. So instead what we do is we couple the spin to the electric component of the microwave photon. In this case, we don't rely on intrinsic spin orbit coupling as we did in gallium arsenide, because in silicon that is actually relatively weak. Instead, we introduce artificial spin orbit coupling by placing a little piece of cobalt next to our quantum dot, and the piece of cobalt produces a inhomogeneous magnetic field. And that means that the effective magnetic field that the spin sees depends now on its position. So that's an artificial form of creating spin-orbit coupling. The spin and the position are coupled to each other. And so with this method, 2 years ago, we were able to achieve the so-called strong coupling regime, where the two branches here in this color plot correspond, well, so out here, you're looking at the transmission, well, sorry, the color scale is a transmission to the resonator, simply put. And out here is just see the resonator resonance frequency around 6 gigahertz. But then when we vary the magnetic field and bring our spin resonance frequency on resonance with the resonator, they don't cross but begin to hybridize. And so these branches that kind of bend off correspond to hybridized states of the spin and the microwave photon. So the two become one object, and their separation is larger than the line width, telling us that we're in this so-called strong coupling regime. And that is the prerequisite to, as a next step, and we're still working on this, to then couple two spins at a distance. So one spin is then at one end of the resonator, another spin at another end of the resonator. And we want to mediate a coupling between those spins at a distance through that microwave photon in the resonator. So that's the challenge that we're working on at the moment. In parallel, we've been working on another approach, which stays closer to just the semiconductor technology, no superconductors involved. In this case, the vision is that we build a channel that connects two registers, and then we push an electron through the channel in a careful way so that its spin state and phase is preserved. And that hasn't been done yet, but what we have done is to show shuttling of electrons inside quantum dot arrays from one dot to the next. And the fringe that you see here on the right shows that after we prepare two electrons in a spin singlet state on the left dot and separate them, moving one electron to the second, the third, the fourth dot and back, that there is still coherence left after this shuttling process. The decay here, by the way, has nothing to do with the shuttling. It's just that in the separated condition, we let them dephase. That's a decay. But so this actually might work. We have not yet quantified the fidelity of the shuttling process, but we're hopeful that especially in silicon, it can be very high quality and high fidelity. Similar work has been done at CNRS Grenoble in the Meunier group and other places around the world. So these are the two approaches we're taking to shuttling. And let me now get to the prospect of integrating the electronics with the qubits. And I want to show two aspects of that. The first is an effort to indeed literally bring the electronics closer. So in all the published literature on spin qubits, the spin states are controlled by arbitrary waveform generators and vector sources that are bulky commercial instruments operating at room temperature. The ultimate vision is that the electronics and the qubits will be integrated together, either on the same chip or perhaps on the same die. On the same package, but possibly on the same chip even. The intermediate step that we've taken is to bring the electronics to 3 Kelvin. So this is now a specially designed control chip by our engineering colleagues at QTech at TU Delft in collaboration with our Intel collaborators. And this chip is specially designed to operate at cryogenic conditions. There has been modeling behind it. And it's actually amazingly sophisticated already, for this first version. And here you see an image of it. It's 4 by 4 millimeters. It actually contains 4 transmitters. So each transmitter is just 2 by 2 millimeters. And it's able to take in a microwave tone and frequency modulated, amplitude modulated, time modulated. It's extremely powerful, this little chip. Operating at 3 Kelvin. And we have, a few months ago, connected it to a 2-qubit spin qubit chip and shown that we can universally control it. We could once again, program algorithms. So the chip is sufficiently programmable. The control chip is sufficiently programmable that we can run algorithms on it, that we can run complex calibration sequences on it. We can shape the amplitude profiles to improve selectivity if we want to. And ultimately what counts, or a way to quantify it, is the control in the end the same as we can achieve with room temperature electronics, or do we here make a compromise? And the answer is we make no compromise. We achieve the same fidelities, and the fidelities were limited by the qubits. We estimate from independent measurements that if the qubits were perfect, this control chip would allow 4 nines of fidelity. At the moment, we don't have perfect qubits, so we can't validate that, but at least that's an extrapolation based on electrical measurements. So this is one side of the coin, but now there is the other side. You know, how resilient are the qubits to temperature? Could we? Well, I think it's unlikely that a lot of electronics can exist at 20 millikelvin. It's going to burn too much power. So then the question is, can we go to a higher temperature where you can burn a lot of power, perhaps 1 Kelvin or even 4 Kelvin, and do the qubits still work? And so this is work that was mostly, well, that was actually done in the group of my colleague Menno Veldhorst at QTech. I was also involved in it, and there's parallel work from the Zurich group, where we have shown that 2-qubit universal control of these 2 spins is possible beyond a Kelvin, with quite respectable fidelities for the first pass and with a lot of room for improvement. We've learned along the way also about how the higher temperature impacts phase coherence and relaxation. For energy relaxation to the ground state, there is a very clear and expected dependence that has to do with an increased phonon occupation by raising the temperature. And then for the dephasing, the main mechanism that looks temperature dependent is charge noise, but other mechanisms appear to be temperature independent even. So we'll see where this, where this brings us, where this trade-off is gonna bring us in terms of the operating temperature. But there is, I think, an opportunity to really make this work all together. So then in the last 10 minutes or so, 10-15 minutes, let me now switch gears and talk about a completely different use of the same physical system of quantum dot arrays. And this is to emulate Fermi-Hubbard physics. And the quantum dot arrays actually implement or embody Fermi-Hubbard physics in a very natural way. After all, electrons are fermions by themselves. There's no encoding needed. The quantum dot arrays constitute a lattice through which the electrons or fermions can move. So that's the hopping term in the Fermi-Hubbard model. And then there is the interaction term given by the Coulomb repulsion for 2 electrons to be on the same site. In fact, we realize an extended Hubbard model because the interactions are not only on-site, but also long-range, as in many relevant systems such as scoop rates or other systems that one wants to understand. There are also long-range interactions in the quantum dot case. And then furthermore, just like we can control the tunnel barrier using the gate voltages, we can also control the on-site potential and the occupation using gate voltages. So these first 2 knobs, on-site potential and tunnel coupling, are gate tunable. The other 2 knobs are mostly set by the design. And what makes this system quite interesting is that in a dilution refrigerator, it is actually possible to access the regime where the thermal energy remains well below, 10 to 100 times below the hopping energy, and where the hopping energy is still below the on-site interaction energy. And that is actually the most interesting regime that you want to be in if you're thinking about Fermi-Hubbard physics. That is the regime where, for instance, in cuprates, D-wave superconductivity occurs. It's the regime where the most intricate magnetism effects occur, and so forth. Of course, there's a lot of work on trying to do this with ultra-cold atoms, other systems, but the ultra-cold atoms, even though they're ultra-cold, it's very difficult to reach this regime where the thermal energy is much below the other energy scales, because these other energy scales in the ultra-cold atoms are also very, very low. In addition, when you put 1 electron in every site of your lattice, there is a lot of opportunity to study a number of interesting spin models. We can imagine triangular lattices looking at spin frustration, quantum spin liquids, and so forth. So it's a very rich system in principle. And this also has been known in principle for a long time. This was just to elaborate more on the powerful experiments done with ultra-cold atoms, optical tweezers, also digital quantum simulation with ions or superconducting qubits. But again, I think the dots really have a special place here because there's no encoding needed for the fermions. They are just there, and we can access this low temperature regime kind of for free. Now this actually was known for a long time that we could do this, except that in practice what we faced is a quantum dot system that is always quite, or has always been quite inhomogeneous, where you need to work hard for a qubit experiment, for instance, to get exactly one electron everywhere. And well, actually that is not so difficult anymore, but certainly to tune all the potentials exactly, to tune the hopping energies exactly, that's quite hard. And after you've done that, if you then want to dial a knob and say, okay, let's now double the tunnel coupling and see what happens. Well, we knew we could do it, but it took time. Not a second, not a minute. It could take an hour or hours or a day, or depending, So what we've had to do in our group and our community has also contributed, several advances, is to learn how to do this efficiently. And now we're at the point where we can, in some cases, really in real time, dial what we call virtual knobs, which are linear combinations of many gate voltages that have a net effect of changing just one tunnel coupling or all of the tunnel couplings homogeneously, or to lower all of the on-site potentials homogeneously, and so forth. And so that's what we've had to learn. And that's what we can now do. And there was a first proof of principle experiment that we did a couple of years ago. You can think of it as a really small scale analog of the metal to melt insulator transition. Let me not, given the time, dwell too much on this, and instead spend more time on another experiment that I'd like to discuss in a bit more detail. And this is the first observation in any physical system of a form of magnetism predicted in 1966 by Nagaoka. And this form of magnetism occurs, or was predicted to occur, if you have a lattice of electrons and you go to half filling, meaning you put one electron on every side, and then you remove exactly one electron. In that limit, Nagaoka could calculate that the ground state should be a spin polarized state, a ferromagnetic state, all the electron spins pointing in the same direction, just removing one electron. It's a form of magnetism that is really itinerant. It arises from the ability of electrons to move around through the lattice, and they can lower their energy more efficiently by moving around the lattice if all the electron spins that are there are aligned, are pointing in the same direction. And what Eugene Demler pointed out to me more than 10 years ago now is that the smallest system in which you could probe this physics is a 2x2 plaquette filled with 3 fermions, with 3 electrons. And so that's what we've tried to build. Here you see a scanning electron micrograph of a device like we've used in the experiment, with 4 quantum dots here in a 2x2 arrangement, 2 additional quantum dots that we use to sense where the electrons are on the lattice here. We worked on the techniques to get homogeneous tunnel coupling between them to control the filling. You see here, a diagram where we change voltages and can go from a completely empty structure to a structure with 1 electron on each of the sides. And then we work hard to go to a particular regime kind of around here where where we have 3 electrons, and then we work really hard so that the missing electron is equally likely to be in any of the 4 sites. That would be the condition that we wanted to go to. Let me try to tell you in brief how we then prepare and measure this system. Let me first tell you how we measure the system. After having gone to this point N, where all the levels are aligned, we bring down the potential of one of the sites, one of the 4 sites, so that this potential is low enough so it can accommodate 2 electrons. But it can only do this if the two electrons are in a singlet configuration. If they're in a triplet configuration, the electrons cannot enter because that, well, the triplet is a higher energy state, and we tune it so that the higher energy triplet is not accessible and the singlet is accessible. So effectively what we do is we go to this condition n, take out 2 of the 3 electrons and then project them in this basis of parallel anti-parallel or singlet triplet. And then we repeat the experiment and we check whether, you know, depending on the conditions, whether we get a lot of paired or aligned spins or anti-parallel spins. The preparation is done at the same point as where we measure, which means we start off with 2 electrons in a spin singlet and then 1 unpaired electron on another dot. And from there, we go to the condition n, either rapidly or slowly. And on the right here, you see an energy level diagram that plots the relevant energy levels on the line that connects the 2 points, the measured or initialization point and this point n. And if we zoom in here, you see that if you sit at this point n, the ground state is indeed the spin polarized state. And if we go in real slowly, we will, you know, these crossings that look like crossings, if you look closely, they're anti-crossings, and they allow you to end up in this ground state if you go in slowly. If you come in quickly, you'll just stay on the same branch and stay in the unpolarized spin state. And so that's what we're going to compare. And what we saw is that coming in slowly, indeed, at this point n, we saw a large probability of having parallel spins. If we came in rapidly, we saw a smaller probability. Notice that if you come in rapidly and stop not at the point n, but a bit to the left or to the right, there is a higher probability for finding the spins aligned. And that is understood because that's where the 2 branches cross. And so you get this mixing of the 2, you basically mix, you populate to some level the spin polarized state. So this all looks consistent with what we expect, but is it really the physics that we're trying to see? We did 3 tests for this. First, we used the tunability of the quantum dot system to turn this plaquette into effectively a linear array by raising a lot one of the tunnel barriers. So the lower tunnel barrier here is so high that it's effectively shut off, and the topology has changed from a closed to an open system, or a system with let's say periodic boundary conditions to open boundary conditions. And in this case, the ground state should be the low spin state, no longer the spin polarized state. And indeed, this difference between pulsing rapidly or slowly has completely gone away, you know, consistent with our expectation. Second test, in principle, if you apply a perpendicular magnetic field, it should be possible to make the spin polarized state go away. And that is kind of curious. Usually you magnetize a magnet by an external magnetic field. Here, a field of just 10 millitesla is in principle sufficient to break the magnetism. And it's because, well, you know, the Nagaoka Ferromagnetism, it's really arising from interference from the electron moving around the ring and lowering its energy. And if you apply a magnetic field, then what was constructive interference becomes destructive interference. And so the ferromagnetic ground state should disappear. We tried to test this. In this case, it was kind of muddled by the fact that we also then have a Zeeman energy. But nevertheless, what we saw was entirely consistent with what we expected. As a final test, we said, okay, our quantum dot system, we worked first hard to eliminate or compensate for the background disorder and align all of these levels as good as we can. Let's now introduce disorder on purpose by lowering or raising the potential of one of the 4 sites on purpose. And let's do this by an amount that exceeds the hopping energy. The hopping energy here was 15 microelectron volts. Well, okay, let's take that energy level, that site, up by 3 times that energy, upwards or downwards. And for sure, then this itinerant ferromagnetism should disappear. To our surprise and initial worry, the difference between pulsing in fast and slow was still there, as you can see. You know, this is going in, let's see, this is going in slowly, this is going in rapidly, with the dot 1 potential lowered, and then yellow the same with the dot 1 potential raised. You see that there are some differences. You know, the difference between these wings, or the separation between these wings, is larger in the green case than it is in the yellow case. But we were really worried now, because we thought that there was a problem, that we were not seeing Nagaoka ferromagnetism. And yeah, what is it then? So here, for this small scale system, it's still possible, of course, to numerically simulate this. And what we found is that our observations actually are exactly what we should have been seeing. It's just that our intuition was wrong, and that this form of magnetism is relatively or surprisingly robust to disorder in the form of shifting a local potential upwards or downwards. And it even works out in great detail. The separation between the yellow wings is smaller, as it should be. Between the green wings here, it's larger, as it should be. In this case, it's reversed, as it should be, and so forth. So in the end, it reinforced our interpretation of the experiment. All right, so wrapping up, this is where we're at with this quantum simulation work. We are now building a ladder and preparing to measure a ladder structure. Ladders are very interesting. They can give rise to pairing physics. At half filling, we hope to explore quantum magnetism, RVB states, perhaps spin frustration. In principle, this system can also give rise to studying many-body localization. There are proposals for that. Discrete time crystals, there are proposals for that. We're interested to study quantum phase transitions and quantum criticality in the system. I think there's a wide field open to explore here. So summarizing, we're now at the stage that the quantum dots have allowed us to see a form of magnetism not seen in any other physical systems before, admittedly on a small scale. And I think that there are many opportunities to continue this line of research. And I'm quite optimistic that this system is well placed to scale to the very large qubit numbers needed for fault tolerance. We're very far away from that, but one step at a time with our community, we're demonstrating the building blocks. And at the moment, I'm not seeing a showstopper. So let's see where this takes us. But again, I think the attractions are that the qubits are very coherent, long-lived. They can be densely integrated into these networks on chip. We can leverage, and it's not just talk now, we've shown it, we can leverage the real semiconductor technology that is going to give us the yield and reproducibility needed for large-scale circuits. And yeah, we're implementing these concepts one after the other. A lot remains to be done, but we're on our way. So obviously, many people contributed to this work, and this is perhaps the most important slide from my own group over the years, but also collaborators for materials, various collaborators for theory, colleagues at QTech and colleagues at Intel that are part of this effort. And so this is where I would like to end, and thank you all for your attention. Thanks.
All right, I think I speak for everyone. Thanking Lieven for a fascinating talk. Thank you for sharing all these exciting developments and really amazing results on small quantum simulators. The session is now open for questions. Please feel free to unmute yourself if you have any. Any questions from the audience?
Hi. Can you hear me?
Yes,
yes, Nancy. Yes.
Yes. Thank you very much for a beautiful talk. I am relatively new to this field, and I feel that I not only could follow your talk, but I learned a lot. So my question has to do with errors in these multiple chips that you are thinking of producing. For implementing error correction protocols, is your idea to do it adding these ancillary qubits that people talk about, or do you have other protocols in mind to implement error correction?
Yeah, it's indeed using these ancillary qubits. And perhaps for those not familiar with the concept, quantum error correction is actually very subtle. Error correction is used in classical technology, and for instance, to send a bit over a noisy channel, you can do it by sending 3 copies of the same bit, or 5 copies, depending on how noisy your channel is, and then do a majority vote, and you'll get a more reliable outcome. But in quantum systems, the no-cloning theorem doesn't allow us to make copies. Furthermore, if we try to measure the system, we perturb it. So we have to be clever. And the way to do it is to use what we call ancillary or additional qubits. And we use entanglement for encoding. And we arrange it such that you do a measurement not on the qubits, but on the ancillas. And the ancilla measurement outcome tells you what error occurred and on what qubit. That's the picture. So you don't measure your qubit because you don't want to. You will perturb it, but you measure ancillary qubits and you learn about the errors that happen on the qubits. And it's really amazing that this can work on paper. There are initial demonstrations of the concepts in a variety of physical platforms, and it is also our what's on our it's going to be our approach.
This will not make the circuits extremely large then?
Yes, they will. And I went over that a bit quickly. And that is exactly the point why, I also forgot to mention, there's a famous experiment that many of you will have heard of, published last year by the Google team, where they were able to control 53 superconducting qubits. And what they achieved is sufficient control over these qubits so that no supercomputer could track anymore what these qubits were doing. But the computation that the qubits were doing was literally computing their own evolution, nothing else. Now, okay, what then? So this was called quantum supremacy. 53 qubits are more complex than what a supercomputer can still capture. From there, it takes a few hundred qubits to go to the smallest relevant problems, but that's only a few hundred qubits if they are perfect, because you need to operate or to implement millions or even billions of operations in sequence. And no qubit is perfect. So then you need error correction, you need redundancy, and the redundancy in the quantum case is very substantial. It's not 1 in 3, it's not 1 in 5, it's more like 1 in 1,000, 1 in 10,000, depending on how good. So that's why we need to go to the millions of qubits, and that's why I'm emphasizing the importance of bringing in the semiconductor technology to have the yield of having millions of working qubits, not perfect, but working qubits, working well enough that you can correct the errors as you go along.
Okay, thank you.
Any other questions? I have a simple, naive question. Is it possible to tune the parameters in your quantum dots such that the interlevel spacing inside the dot due to confinement is of the order of the Coulomb repulsion between electrons?
So we would tune it not by the gate voltages, but more by the design. And so the dependence on the size is different for the orbital quantization energy and for the charging energy, and that's where in principle, yes, you could reach that regime. To give you an idea, in gallium arsenide, typically we have orbital energy spacing of about 1 milli-electron volt and charging energies of a few milli-electron volts. So it's actually not that far away from the regime that you're talking about. And yeah, with the modified design, you can reach it. You can also reach it if you use a different semiconductor where the effective mass is different. That also, of course, changes your level spacing, keeping everything else the same. Yeah, or you can change, or you can put more metal nearby and reduce your charging energy, etc. Yeah.
Right. Any other questions from the audience?
Yeah, can I have a second question?
Of course.
Thank you. So going back to the strong coupling regime that you are implemented between the spin and putting a cobalt atom nearby. So I have the picture that
cobalt magnet, yeah, it's a micron scale magnet. Yeah.
Okay. So my question is even more to the point. So I imagine that you would like to do that for each spin, right? Which means you will need to have a lot of cobalt magnets nearby to each of them. Aren't they going to create fields not only for the spin that is nearby, but for the other one? So I am trying to picture the spacing. Yes. And the screening, if you want, of the field, so you can make sure that you are attaching this inhomogeneous field to the spin that you want.
Yes. So I think the cobalt or other, magnetic materials, the micromagnets are lend themselves quite well to one-dimensional arrays up to tens of, even in the end, it doesn't matter how long. So for linear arrays, they work well. For two-dimensional arrays of, let's say, n by a few, they would also work. For, let's call it 20 by 20 densely packed qubits, I don't think that it's going to be easy to get the right profile from these micromagnets. In that case, we would rather use magnetic driving, so oscillating magnetic fields, and not rely on this cobalt micromagnet. Yeah.
Mm-hmm. Mm-hmm.
I have a quick question. So presumably the Nagaoka ferromagnetism simulating thing you do requires just a handful of qubits. So what is the advantage of fabricating your own circuit with Intel and all of that to actually do the simulation rather than using one of the sort of like handful of commercially available quantum hardwares?
Well, let's see. So I first wanted to clarify that the only experiments where we have used quantum dots fabricated at Intel is this one here, and so everything else that I've shown is done on locally made, well, in Delft in our cleanroom made quantum dots. Mm-hmm. So now to your question of the Nagaoka ferromagnetism, is your question why not use a superconducting processor, for instance, to study this form of magnetism, or an Eintracht processor? Is that? Yeah,
essentially.
So actually, to do that with qubits and then encode fermions in the qubit state would be quite involved. It's 3 fermions moving on 4 sides, and then if you account for the fact that you include perhaps some orbitals, then the Hilbert space quickly becomes very large, and mm-hmm. and to program that on a quantum computer would already be quite demanding. The only other system that I can think of that can see this form of magnetism are the ultra cold atoms. So from talking to Marcus Greiner or Emanuel Bloch, they think they also could do it. They haven't done it. They haven't created the conditions or the type of lattice that is needed, but they think that there is no obstacle in principle, and they could do it.
Okay.
Any other questions? All right. If not, let's thank Lieven one more time. Thank you for being here with us. Appreciate you for staying late in Europe, also to the audience overseas. And we're looking forward to seeing you again next week for our next Quantum Matter seminar. Thank you, Lieven.
Thank you very much. Bye-bye.
Bye-bye.